In this video, I will show you how you analyze the result of a potential energy surface scan. So I have done a potential energy surface scan along the dihedral angle defined by hydrogen-carbon-carbon-hydrogen atoms, which corresponds to the rotation of methane, to the internal rotation of methane. Here is the result of my potential energy surface scan. You can see that I have 37 different geometries here, and when I click on the green circle, I can animate the motion of the molecule, and you can see the rotation of the methyl group. So do the right click on the background, go to Results, choose Scan, and here you can see the plot of the total energy with respect to the scan coordinate. So I will do the right click, Properties, and I will plot this in terms of kcals per mole. So I will change the units to kcals per mole and choose one of the minima that I have on the potential energy surface and set origin to 0. So click on Current, click OK, and I'm going to also hide the other plot. So click on Hide Other Plots here. Okay. So now you can see the potential energy surface scan. I have 1, 2, 3 minima. Please note that this fourth minimum, this point, is identical to this point here. So I have 3 minima and 1, 2, 3 maxima. The minima correspond to different stable conformations. I can make sure that they are really different. So do the right click in the view window, click on View, and let's choose labels here. So these labels my atoms. So you can see that this first minimum corresponds to the conformation where hydrogen 3 is in between hydrogens 8 and 6. When I move to the next minimum, now you can see hydrogen 3 is between hydrogens 8 and 7. And the last minimum, the hydrogen 3 is between hydrogens 6 and 7. When I go to this minimum I have at the end here, again you can see that hydrogen 3 is between hydrogens 8 and 6, which is identical to this beginning point. Okay. So all of these minima correspond to 3 different staggered conformations of ethane. You can choose one of the maxima, and you can see that now I have an eclipsed conformation of the ethane molecule. And again, these atoms are moving, so I go 6 is eclipsed with 2. When I go to the next one, 6 is eclipsed with 3, and the next one, 6 is eclipsed with 4. Okay. So the minima correspond to stable conformations, maxima correspond to transition states on my potential energy surface. Of course, these are just approximations to the transition state, and this is not necessarily the exact minimum conformation for my molecule, but it's somewhere in the neighborhood of the real minimum. So if I want to find the real minima and if I want to find the actual transition states, I have to perform structure optimization or transition state optimization to find the transition states. So before I show you how you perform a transition state optimization, I'd like to point out that the barrier to rotation of methyl group in ethane is really small. You can see, looking at the y-axis, the maximum is somewhere between 2.75 and 3 kcals per mole. So the methyl rotates almost freely in an ethane molecule at room temperature. Okay, so how you go about setting up a transition state optimization? So pick one of the maxima from the potential energy surface scan, then click on New, and what I'm going to do is to copy and paste this conformation that corresponds to the maximum. I can close the plot, do the right click on the background, go to Edit, Copy, and left click in my new window. Okay, so I have here one of the staggered conformations for ethane. Now I'm going to go to Calculate, Gaussian calculation setup. For the job type, choose optimization and frequency. And now I don't want to optimize to minimum, but I want to do a transition state optimization. So click on minimum here and choose TS with Bernie in parentheses. Go to Method. I want to do this at the DFT level with BISRAEL YP functional. For basis set, choose 631G D. This is neutral molecule, spinny singlet, so this is looking good. Let's go to title. So this is ethane transition state optimization. Let's see. For link 0, I want to specify 2 GB of RAM, 2 processors, and I will need to add some additional keywords. So in this window that says additional keywords, types opt equals calc fc, comma, no eigen test. So what this will do is to calculate the force constants on the beginning of transition state optimization, which essentially corresponds to doing vibrational analysis for my molecule. And no eigentest means that it is not going to test for a certain condition that needs to be satisfied for Bernie optimization to proceed. Okay, so now this looks ready. So let's go to preview. Okay, so again I have my root section. Now OPT equals TS. This means that I will run transition state optimization followed by frequency calculation, my functional basis set, XYZ coordinate. So everything is looking good. So I can go ahead and submit. Click on submit, save. I will call this ethane TS OPT .gjf. Click on save, and I will submit to Gaussian. So this will take a little bit of time to complete. So now my scan is complete. I will open the log file. Click on open. And here is the result of transition state optimization. To check if I have really optimized the structure to a transition state, do the right click, go to results, and choose vibrations. So what I want to look at here are the frequencies in wave numbers, the second column here. You can see that all of the frequencies are positive except one that is negative 304 wave numbers. So that's what I want to see for a transition state, that I have exactly one negative frequency. Next, what I want to do is to animate the frequency to see if it corresponds to the coordinate that's defined by the internal rotation of methyl. So click on Start Animation, and you can see that this indeed corresponds to the methyl rotation. So I have successfully optimized that transition state for internal rotation of methyl.